Stoichiometry is based on the law of conservation of mass. And so if that sounds familiar, it's because we use the same exact argument when we were talking about why equations need to be balanced in the first place. Well, all that we're doing in stoichiometry is applying an additional layer of calculation onto what we already did in chapter 2. So chapter 2, we did all those mole conversion things, turning masses into moles, turning particles into moles, turning masses into moles of elements, or eventually empirical formulas. Stoichiometry basically says, okay, well, all those calculations we did in chapter 2, those are great. Why can't we take it a step further? Why can't I take what I know about carbon dioxide and use it to figure out how much butane I had in the first place? Why can't I cross between one compound and another? The thing that was stopping us then is because we didn't have a relationship between one compound and the other. But now we do. The relationship we have is the balanced chemical equation. Balanced chemical equation says, oh yeah. Butane, yeah, every one of those that burned, I got 4 carbon dioxides. Now I have a relationship between the two. Now I can tie the two together chemically and mathematically. And that's all that we're asked to do in stoichiometry, is use that balanced chemical equation to help us establish relationships between compounds and each other in a chemical reaction. So we can't do this without a balanced chemical equation. That's why we spent all that time talking about equations and balancing leading up to this. But as far as calculations go, there aren't that many there. Yes, we need a mole ratio coming from the balanced chemical equation. But the other things that we need are things we already know how to do from chapter 2. We already know how to take molar masses using the periodic table. So what's holding us back? Process. We need to know how to tie the things together. And luckily, we have a process that is in place. Now, this should look a little familiar. We use a very similar looking map in chapter 2 to get us between elements within a compound and the molecules of the compound itself. The only thing that's different is that instead of going within the same compound, we've now separated one compound, which for lack of a better term, we're going to call A, and another compound, which for a lack of a better term, we're going to call B. And the relationship between A and B comes from the middle, the balanced chemical equation. So this mole map is an organizational chart, just like the chart was in chapter 2. So if you got use out of that chapter 2 chart, this is more or less the same kind of idea, just tying together those concepts. And what this allows us to do is, if we are presented with a problem, now we can tie it together. Let's say I want to know the number of grams of one substance based on the moles of another. Well, I can clearly see, using this map, that there is going to be a 2-step calculation involved. Using the balanced equation, I can turn moles of one substance into moles of the other. And using the moles and the molar mass, I can turn moles of that second substance into a mass, just like we did in chapter 2. So the calculations here are identical to chapter 2 calculations. The only difference is the use of that balanced equation. Let's take a look at a practice problem. So we're told that we have 13.33 grams of aluminum, and we burn that aluminum in excess oxygen. What mass of aluminum oxide would be formed as a result of the reaction? So we want to go from 13.33 grams of aluminum into some number of grams of aluminum oxide. Since we are crossing the barrier between reactants and other reactants or compounds, we're going to need to use the mole map. We're going to need to do stoichiometry, which means we need to have a balanced equation. So we've got aluminum reacting with oxygen to make aluminum oxide. If we balance this out, 3 oxygens means we need 2 aluminum oxides, which means we need 4 aluminums. There's my balanced equation right there. How do we actually go about solving the problem? Well, again, this is where our mole map comes in. So we have established a balanced chemical equation relating the 3 substances, aluminum, oxygen, and aluminum oxide. We are starting with 13.33 grams of the aluminum, and we're trying to figure out how many grams of aluminum oxide are going to go into that product. Following the mole map, we can see there's no way that I can go directly between the two. I can't convert the aluminum into aluminum oxide with one simple calculation. There's no connectors between grams and grams, at least not in a single easy step. What I'm going to have to do instead is I'm going to follow the map and go, okay, how do I go from grams? I need to go grams to moles. Then using the balanced equation, go from moles to moles of aluminum oxide. And then from moles of aluminum oxide, I can go into grams. So in summary, I'm going to have 3 steps. First step, I need to convert the mass of aluminum into moles. Second step, I need to turn the moles of aluminum into moles of aluminum oxide. And then finally, I'm going to need to convert the aluminum oxide into grams. As I did in chapter 2, dimensional analysis, unit conversion is the easiest way to go about do this. Do it all in a series of sequential steps, just one conversion after the next, and round everything at the very end so that we don't get big rounding errors when we do our significant figures. So putting it all together now, I have rewrite my balanced equation here. We have 13.33 grams of aluminum I know I need 3 steps, so I'm just going to write them all here. Grams of aluminum into moles is my first step. I go to the periodic table. Periodic table tells me that the mass of aluminum is 26.98 grams. So 1 over 26.98 grams of aluminum cancel. My second step is to take moles of aluminum and convert it into moles of aluminum oxide. Balanced chemical equation gives me the relationship 2 aluminum oxide for 4 aluminum. So my moles of aluminum cancel. And then finally, last step, 1 mole of aluminum oxide. Need the molar mass, 2 times 26.98 for the aluminum, 3 times 16 for the oxygen, 101.96 grams of aluminum oxide for every mole. Everything cancels. We're left to this last part, 13.33 times 2 times 101.96 divided by 26.98 divided by 4 to 4 significant figures, 25.19 grams of aluminum oxide. So these calculations are really simple. These are an extension of what you did. You did this kind of conversion and this kind of conversion in chapter 2. The only one that you didn't do was the one in the middle. But if you have a balanced chemical equation, it's just a matter of putting the correct coefficients in the correct places. So even at that, it's an extension, but it's not that earth-shattering or mind-blowingly difficult. It's just knowing when to do what you need to do. Any questions with this example? All right, let's do one more and then we'll call it a day. And so 2 things are going to happen. After this example, I am going to push the deadline for assignment 7-2 to Wednesday as well. I encourage you to still try to do it, but since we're not going to get fully into limiting reactants, you may struggle a little bit. The other thing I'm going to do is I'm going to put a supplemental video up covering limiting reactants, and I encourage you to watch that because when we come in on Wednesday, I'm going to talk about yield percent, and we'll do a couple of review problems, and that will be it for chapter 7. I'm not actually going to explicitly discuss limiting reactants. So I'm going to add a little bit to that assignment 7-2 just to help get us caught up a little bit so that we're not blurring through and starting to cut into chapter 8, because we're going to want a good chunk of time in chapter 8. It's a very long and complex chapter. We don't want to start shaving days off of it to handle calculations that are not too difficult that we can't handle with just some extra time and practice. So we've got our balanced chemical equation for the reaction between cuprite and charcoal. We need to know how much carbon is needed to prepare a 256 gram copper bracelet. So starting with our given information, we have 256 grams of copper. Now, we want to know how much cuprite and how much carbon are going to be necessary. So what we're going to do is we're actually going to split this into two pieces. The first conversion is going to be exactly the same. 63.55 grams of carbon, or excuse me, copper, in every mole of copper. That part's going to be identical in both of these. So if I do that conversion, I will get that we are going to need to make 4.03 moles of copper. Now, why did I stop here? Well, because that's where this common thread diverges. For the cuprite, we would have moles of copper turning into moles of cuprite. The relationship there is 2 to 4. And then 1 mole of cuprite, 63.55 times 2 plus 16 is 143.10 grams. To turn it into copper, carbon, 4 moles of copper is 1 mole of carbon. 1 mole of carbon is 12.01 grams. And so if we complete each of these calculations, we would need 288 grams of cuprite and 12.1 grams of carbon to complete the reaction.
Let's talk a little bit about limiting reactants. So with limiting reactants, what we're dealing with are stoichiometry, where we have to ask a really simple question, and that is, do all reactions actually go to the completion? And the answer there is, well, yes, of course they do, but that doesn't necessarily mean that everything that was a reactant turns into a product. So let's take a look at a simple example. Let's say that we are burning charcoal. Carbon in the presence of oxygen makes carbon dioxide. So that's basically what happens when charcoal burns. Now, if we were, say, to ignite a brick of charcoal in a big open room, it would be pretty safe to assume that all of the charcoal would burn, right? It'd be very unlikely that it wouldn't. But we also understand that if we took that same brick of charcoal that was on fire, put it in a jar and closed up the jar, charcoal probably would eventually snuff out. The fire would stop and there'd be a bunch of unreacted charcoal left over. So what gives there? Why is it that we can have a reaction going 1 minute and not the next? Well, what it comes down to is our understanding of limiting reactants. So we need to look at some terminology here. First of all, what is a limiting reactant? Well, a limiting reactant is the substance, the reactant, that ultimately limits the amount of product that you can make in a chemical reaction. So in the case of that charcoal example, when we lit the charcoal inside of the big room, well, the charcoal didn't run out, but chances are pretty good there was oxygen still in the room after we did the reaction. And if it didn't, then we would have problems of our own for being in the room that was lit with the lit charcoal, because we need oxygen to survive also. So limiting reactants do have an impact in that kind of way. So every reaction that we can think of has a limiting reactant, something that is going to run out first. And once we run out of that substance, the reaction as we know it stops. When that happens, there's usually an excess reactant, something that we had more than enough of. And as a result of having more than enough of it, there's left over when the reaction is done. That's what makes it excess. Now, it is possible that you can have both substances in a chemical reaction be limiting reactants. If we do a reaction and we measure out everything very, very precisely, and we do the reaction and all of the reactants react and there's nothing left over, what that is called is a stoichiometric amount. That's basically the exact amount that we need to do the chemical reaction. Now, the only way that we can get stoichiometric amounts is by measurement. And that usually involves calculations of stoichiometry, which is why it's called a stoichiometric amount. But I want you to think about this another way, possibly. Maybe something that's a little bit more familiar. Let's say that for the sake of argument, that we have a hamburger store, and I'm going to pick on Wendy's here because Wendy's was my first job in college, and they have a soft spot in my heart, not because I was the best worker or that they treated me, particularly well. They treated me like any other job did, but mainly because it was my first. Now, let's say that the whole idea of customization is out the window, and this is how you make a cheeseburger. Cheeseburger has a bun, it has a hamburger patty, it has a slice of cheese, it has pickles, it has onions. That's what we're going to make today. That's what we're doing when we sell cheeseburgers. Well, each of these substances, the bun, the patty, the cheese, the pickles, and the onions, we can think of as reactants in this rather complex equation to make a cheeseburger sandwich. The question I would have for you then is this. If Wendy's has all of these ingredients in tow, and the recipe is as follows, how many cheeseburgers could we ultimately make? So if I only have 13 buns, if I have 5 pounds of hamburger meat, if I have 25 slices of cheese, if I have 100 pickles, if I have 30 onions, how many cheeseburgers would that make ultimately? So take a second and just sketch it out somewhere. Try to figure out what it is that you're going to do, how many cheeseburgers you can ultimately make. And I will reveal the answer here in 5, 4, 3, 2, 1. So the answer here is actually relatively simple. We can just take those ingredients, figure out how many burgers we can make with each of them, and then we know that whichever one runs out first, well, that's when it stops. So the 13 buns, well, we know we can make 13 burgers out of that. Since each burger has a quarter pound of meat, that means I can get 4 burgers out of every pound of meat. I can make 20 burgers with all the meat. With the 25 slices of cheese, I can make 25 burgers. With the pickles, I can make 50. With the onions, I can make 10. So when all is said and done, the end result is I can make a whole 10 burgers with all of the cheeseburger material that I had previously. And that's an important thing to know. because under our definition of what a cheeseburger is, I can only make 10. Now, anyone could look at this and say, okay, well, hold on a second. You're going to have a few buns left. You're going to have some meat left. You're going to have some cheese and pickles left. Couldn't you make cheeseburgers with those remaining ingredients? And the answer is yes, to a degree, but they wouldn't be the kinds of burgers that were specified in the recipe. And the same thing exists in chemistry as well. With the excess reactants, could you make more stuff? The answer, of course, is yes. Yes, you could, but it would not be the same stuff that the original chemical reaction was intended to make. And so under this example, onions are going to be the limiting reactant because they're going to be the thing that we run out of. Everything else is going to be in excess. Now, something else that we can look into and that we can look for is, well, if I make those 10 burgers, how much of the other stuff is left over? Well, I can see that there will be 3 buns. I can see that there will be 10 burgers worth of meat. I can see that there will be 15 burgers worth of cheese. And I can see that there will be 40 burgers worth of pickles that are all left over. So again, all of those excesses, could we turn them into something? Absolutely. Would it be the same thing that we were making in the first place? No. So how do we apply this information? Well, if I'm given a limiting reactant example, so what I mean by that is, let's say that I am given a practice problem, and that practice problem requires us to determine which reactant runs out first to determine how much product is made. Then what we can do is very similar to what we did in the Wendy's example. We take the reactant, convert it into product, and we do that for every single reactant. The reactant that makes the least product, that's our limiting reactant. That's also how much product is made by the reaction itself. And so that gets us to something that we're going to refer to in a little bit here as the theoretical yield. So more on that in a little bit. So let's take a look at a chemical example problem here. So here we're told that we have acetylene and oxygen, and we have 52 grams of acetylene, 188 grams of oxygen. What we want to know is, what is the limiting reactant in the reaction between acetylene and oxygen? So before we can do anything else, first thing that we have to do is establish the balanced chemical equation between the two. And recognizing that this is a combustion reaction, we have a hydrocarbon reacting with a oxygen. We know that carbon dioxide and water will be our products. And so now, just as a matter of balancing, I'm going to need 2 of these and 4 of these. And so 4 times 2 is 8, 2 times 1 is 2, 8 plus 2 is 10, so I need 5 oxygens. So there's my balanced equation.
Chapter 7, we kind of spoke of already. When we did empirical formulas back in chapter 2.
So we've got our balanced chemical equation now. Now it's a matter of what we do with it. And so again, like the Wendy's example, what we're going to do is we're going to take our 52 grams of acetylene and we're going to turn it into grams of one of the products. It doesn't say which, we're just going to go with carbon dioxide. And we're also going to take the 188 grams of oxygen and turn it into grams of carbon dioxide as well. Now, two things are important here. First of all, we want to make sure that we have the correct masses and the correct substances. The other thing that is important in a limiting reactant problem is we want to make sure that we are converting to the same substance and the same unit. If we don't do that, we are going to have major problems with our analysis. So make sure that we are converting to the same thing before we do all the calculations. If we end up getting different things here, we can't make an honest comparison of them. They're going to come out wrong. So start with the acetylene, 12.01 for carbon times 2 plus 2 times 1.01 for hydrogen is 26.04 grams of acetylene in the 1 mole. And then we're going to go from moles of acetylene to moles of carbon dioxide. The ratio there is 4 to 2. And then finally, from moles of carbon dioxide to grams, carbon is 12.01. Each oxygen is 16. There are 2 of them. 44.01 grams in a mole. Do all of my canceling outs. I get 52 times 4 times 44.01 divided by 26.04 divided by 2 to 3 significant figures, 176 grams of carbon dioxide. Now, we have no idea if that is big or small, at least not until we actually do the conversion and see what the oxygen does. For oxygen, 32 grams in 1 mole. 5 moles of oxygen for every 4 moles of carbon dioxide. And 1 mole of carbon dioxide is the same, 44.01 grams. So you can see the last step in both of these conversions is exactly the same because, again, we're going to the same product, and that's important. It should be the same. So grams cancel, moles of carbon dioxide cancel. I'm left with just grams of carbon dioxide, 188 times 4 times 44.01 divided by 32 divided by 5. 3 significant figures, we get 207 grams of carbon dioxide. So important things to know here. Based on this result, we are getting less carbon dioxide with the acetylene than with the oxygen. So that means that our acetylene is the limiting reactant. It also means that the oxygen is our excess reactant. And then finally, it also means that our theoretical yield for the reaction is 176 grams. Because again, whatever the limiting reactant yields, that's what we should expect as far as our product is concerned. Now, there is one other thing that we could be asked to do. This might show up on one of your homework problems, might even show up on an exam. So be aware. What do you know about the oxygen that's left over? So what if you wanted to try to figure out how much oxygen was left over after the reaction was done? So there are a couple of ways that you could do this. The easiest way is take these 2 products and subtract them from each other. So we can find out how much excess oxygen there is by doing this. If we subtract the masses of the two products, what that would give us is an amount of excess carbon dioxide. Now, all that we have to do from there is basically just work backwards. So take this bottom equation, this bottom reaction calculation, and run it back the other way in the opposite direction. To get our mass of excess oxygen. So if I did that, 31 times 5 times 32 divided by 44.01 divided by 4, two significant figures this time, we would get 28 grams of oxygen. So 28 grams of oxygen were left over. That means that 160 grams reacted. And so, again, that's not going to come up in every limiting reactant problem, but for the ones that do come up, this will tell you how to do it.